What is going on, ladies and gentlemen? It is Jake, aka StarCoding, coming at you with another video where we're talking about computer science. You know, the mantra of the show is shining light on code, and I figured I'd take a look at some of the fundamental things that make up computer science. And what I'm talking about here is Boolean Algebra. So this video is going to be for people that are just getting into the field, getting into, IT, computers, software engineering. If you're in high school, if you're in college, you may be taking a course where you're talking about this thing called Boolean Algebra, and it might not make sense in the sense of like, why should I learn this? Like, what is adding these symbols really doing for me as a future programmer? That is what this video is all about. So, we're talking about Boolean Algebra, and when you're taught it in school in a course, usually you just get thrown some laws, just a list of laws, and you're like, okay, this is kind of cool. Essentially, if we take a closer look, it's really close to regular math. I mean, we have this like commutative law, which looks a lot like, when you're adding two numbers, a plus b, x plus y is equal to y plus x. It doesn't matter the order. You have this associative law, which deals with parentheses and how you distribute things when they're multiplied together. There's some other things in here, the law of intersection, the law of union, a lot of good things here. Let's get a marker out, that way we can actually draw on this thing. You have this distributive law as well. And yeah, there's a lot of things on this list, and what do they mean in the real world? Well, a lot of these things, when I'm talking about this commutative law, this associative law, this distributive law, these things, they happen in math, they happen in every algorithm that you make, pretty much. It's just the laws of numbers, and so that's going to apply to logic and variables. When we talk about Boolean algebra, we're talking about zeros and ones and how they interact with each other and how we can do cool things with them. And if you can imagine a 0 and a 1, kind of the basic rules of algebra are going to apply to them. But there's a little bit more that we can do with these numbers. And what we're going to look at first, so the first example that we're going to show that kind of uses Boolean algebra in the real world is databases and sets. It's not necessarily using one of the laws that was listed, but the operations that are usually used in Boolean algebra, there might be some and statements, some ors, some nots. Where those statements are always used and what makes them great is in sets. And so when we're like looking at a database, when we're querying for specific information, we have a pool of data, we have a pool of users that exist in this world, and I want to get a set of those users. And so, if I wanted to send a reminder email to a group of users, and this users is a big ocean, it's a big vast ocean of objects, how am I going to do that? Well, I might be inclined to grab the users who have not received a reminder email, and then I also might be inclined to get the users that have email notifications enabled. And if I take the conjunction of these two, if I take the and statement of these two, what I will get is my result. Simple enough. Nothing too crazy here. And so what we're really just saying is, if this was A and this was B, if I took A and, which is usually, a, I guess, bottom turned over U, or maybe sometimes it's denoted as a V or a U. If I took A and B, I would get something, and that something would be my result that I'm looking for. And so that is kind of, where we're going to start with these real-world implications. Databases and set theory is all about, these logical operations. So the second thing we're going to talk about is TCP/IP. And this is kind of something that we can all relate to, something we all see on the daily. And if we look back up, we're going to be primarily looking at this law of intersection, which is, A and 1 is equal to A, A and 0 is equal to 0. A can be 1 or 0, you know, so whatever A is, if you times it by 1, it's just going to get whatever it is. If you times it by 0, and when you have these like times, it's kind of like anding in my mind. That's just how I interpret it. Fun fact. But if we look at TCP/IP, we have these things called routers. And not to get too crazy into networking, essentially what a router is going to do is it's going to get a packet, and it's going to, you know, distribute it to a certain location depending on what the IP address is. Now, you know, when it comes to these routers, they are super efficient. They are delivering millions of packets a second. It's why you're able to watch this YouTube video right now in high resolution, I hope. So how are these routers doing things so quickly? Well, for one, you know, the router doesn't need to look at the entire IP address. It just needs to look at a subset of that IP address. For example, we have this guy up here, 192.168.0.1, typical IP address. And I need to know where that IP address should go. And the router is going to have, you know, some tables that it might send it to. It's going to try to match a subnet mask to that IP address and send it there. Don't worry about the terms. Just know that there's like some pattern recognition that the router wants to do, and it's going to use that law of intersection to do this. So we had that IP address, you know, 192.168, and so we can look at the router. Okay, like this is where it obviously wants to go, but it would check through its table of routes that are possible. So it might check, is the IP address, you know, 50.50? Is it 100.100? No. Is it 192.168? Oh, it is. It does start with this. And so that operation that takes place is, you know, it might seem easy at first, like, okay, yeah, obviously it starts with 192.168, so it's going to go there. But how do we do that in an efficient way? Well, we can take this IP address and apply a mask to it, which is really just a bunch of ones. So every time I see this .24, this mask essentially is how many zeros we're going to have out front. And technically, now that I'm looking at this, this should be, if I can edit this guy. Okay, we can't edit it, but we can cross it out. This should be a .16. So I am going to make a mask of 16 bits and do an AND operation on those first 16 bits on every packet that comes to my router. And the ones that are accepted in this operation, the ones that return this result, I'm just going to send to that next hop, and that's all I care about. So what the router is really doing is just taking the IP address, applying some sort of mask to it, and comparing that value. It doesn't care the finite details. It doesn't care about that 0, that 1, or whatever address it is. It just cares about that mask, and then it sends it off. And then a router, you know, hopefully in your home, the router at your office, is going to take that packet that eventually arrives and then send it to the individual person. So that's how that kind of takes place. So the third real-world application that I want to talk about with Boolean Algebra is circuits. When we think about smartphones, computers, printers, all the functionality that these devices do is carried out through electricity. And that's just ones and zeros. It's just gates on a circuit, which sounds a lot like, you know, Boolean Algebra. And so let's talk about how one actually adds two bits together, how that actually looks in practice. Well, we have a circuit down here. It's called the half adder. And what it's going to take is a AND gate and an XOR gate. I'm not sure if you're comfortable or have heard of an XOR gate, but we're going to talk about it in just a second. Let's just like walk through this if we were adding two numbers together. Like 9 plus 2, okay? If I'm adding 9 plus 2, in my mind, sometimes I'm like, okay, 9 and 2, that's equal to 1. Although, you know, on the surface it doesn't seem like that. But then you tell yourself, okay, I'm going to carry over 1 which is technically 10. I'm going to carry over 10, and I get 11. Same thing, you know, if I'm taking 7 plus 5, technically that's equal to 2. I carry over 10, and I get 12. And so we're going to do the same thing by adding two numbers together, you know, in base 2, and we're going to have a carry bit in case it goes over. Now let me just erase this that just went down. So if I come down here, essentially what we got going on is we have our variable A and our variable B. This is a truth table, and A can either be 0 or 1, and B can either be 0 or 1. And so if I'm adding 0 and 0, obviously I'm going to get 0. If I add 0 and 1, I'm going to get 1. If I add 0 and 1, I'm also going to get 1. If I add 1 and 1, technically I get 2, but that is going to equal 0. Essentially, for what the computer knows, it can only represent a 0 or a 1, and so that, you know, 2 can't really get represented. But what it can do is we can add an extra gate, which is kind of called the XOR operation. And what that is going to do is it's going to say, is A and B the same? If A and B is the same, it returns 1. If A or B, it doesn't care. If they're both 0, it doesn't care. So you could essentially say, hey, if I have A and B being added together, that means that A and B are the same, and this carry bit is represented by that XOR operation. I didn't have it drawn on this table, but I hope that just talking through it kind of makes sense. You can give it a Wikipedia lookup as well. So that is going to do it for 3 real-world applications of where Boolean algebra is used. I hope you found this video useful. And as always, subscribe. Thanks for watching. I'm also going to leave a link to a Discord channel below. Feel free to join the community. Take care, guys. Peace.